Okay, today we will start a new chapter, and the name is Z-transform. Honestly speaking, Z-transform, together with perhaps the Laplace transform, are the cheapest deals that you can get for the final examination, because the content is quite coherent. It's easy to understand, it's not very complicated, and once you understand the Laplace and the Z-transform, you'll be able to solve a majority of the questions in the final, because those are the latest topics. So I recommend that you pay attention to this new topic, the Z-transform, and try to understand it well. So let's write the name of the chapter first. Z-transform, and it corresponds to the Laplace transform in discrete time, because Laplace transform was a transformation for continuous time signals x of t. Now we have x of n, and what's the corresponding transformation for that? First, let's see what we did in the Laplace transform. We said that we assigned a new variable s, which has a real part as well as an imaginary part. Imaginary part was governing the frequency content, j omega. Sigma was more related with the region of convergence, suppression or expansion of the exponents. Now, in the discrete time Fourier transform case, if you remember, the Fourier transform that we defined was something like this. It was capital X of e to the j omega. You remember that? Because that was the notation. And it was equal to a summation over all x of n multiplied by e to the minus j omega n. Okay. Now, what we're going to do is we will augment the j omega variable over there, e to the j omega n, in that variable, with sigma plus j omega again. So the context is quite similar. It's not very much different. We'll say something like this: x of e to the sigma plus j omega, or you may think of it like e to the s expression, and that will be equal to x of n e to the minus sigma plus j omega n. So this will be our new notation. But this new notation is too complicated, because the Fourier transform in discrete time is too complicated. It's in the exponent. It's not x of j omega. It's x of e to the j omega. And by adding a further sigma real variable to that, we'll complicate things even further. So we assign some new things to this. We will say that e to the sigma plus j omega will have two parts. Like sigma and j omega, e to the sigma plus j omega has two parts. That is e to the sigma times e to the j omega. This e to the j omega, well, we know what it is. It's a complex exponential. This e to the sigma is a real value, and that real value is always between 0 and infinity, no matter what sigma may be. You see? Because if sigma is negative, or between 0 and 1, or greater than 1, whatever, in all cases e to the sigma will become something something positive. And that positive thing, we will understand the reason. It will correspond to the radius of a rotating entity. That rotating entity is e to the j omega. Okay, it's a rotation. E to the j omega is a rotation. If omega is equal to 0, it will show the 0 degrees. Then pi over 2, or 90 degrees. Then 180 degrees, pi, etc. And then when it comes back to 2 pi, e to the j 2 pi is equal to e to the 0. You come back. So a sinusoid, an oscillation, can also be imagined as a rotation, as you may see. So that rotation will be the circle that we have. So e to the j omega will correspond to a circle. And e to the sigma will correspond to the radius of that circle. Because originally, without that e to the sigma, e to the j omega by itself will have a radius of 1. Because the magnitude of that one will be 1. But the altogether magnitude will be r times 1. So the new oscillation will be r times e to the j omega. So this is our new notation, and we will have a shortcut for that, and that's where the name comes from. That will be z. You see that the new variable z is also complex. It's a complex variable. But it's not sigma plus j omega. It's e to the sigma plus j omega, which corresponds to r times e to the j omega. And that r is the radius, e to the j omega is a circle. We also call it a unit circle because the radius is 1. Of course, using the Euler's expansion, you can expand e to the j omega into cosines and j sines, and then you will see that it's indeed a complex entity. So just like the S-plane, the Laplace plane, where the real axis corresponds to the horizontal one and the vertical is the imaginary axis, we will again have a complex axis, and we are going to call it the z-axis this time. And guess what? On the z-axis we will have poles and zeros, quite similar to poles and zeros in the S-plane. Okay, so what can we say about the z-transform then? The z-transform can be reformulated like this. E to the sigma plus j omega is r times e to the j omega, and in that parentheses argument, therefore we have x of z, and x of z is equal to, for all n, summation x of n times. Now, can you relate the top right corner, e to the minus sigma plus j omega n to z? Can you relate that to z? What does that say? E to the sigma plus j omega is z. So what is e to the minus sigma plus j omega times n? It is z to the power minus n with a negative sign in the exponent, and that is the nth power is taken, so the exponent is multiplied by n. Okay, do you all see that? So this then automatically becomes our new transformation formula, which is the z-transform. And this z-transform, without going to, before going to the examples, we will see later why it really corresponds to the time domain representation itself. You see that the this summation will induce some z polynomials, z to the minus n for all n. Suppose that x of n has finite duration. It starts at n is equal to 0 and ends at n is equal to 10, for instance. Then what kind of an expression does x of z have? It will have expressions like something times z to the 0. Z to the minus 0 is z to the 0, which is nothing, 1. So then we will have another coefficient that is plus x of 1, which is another value, times z to the minus 1, plus something else times z to the minus 2, plus something else times z to the minus 3. So z to the minus 1, z to the minus 2, z to the minus 3, etc. will contain or will formulate our polynomial, z polynomial. Conversely, we will have, we may have some negative n's, because that summation of over n may start from minus infinity and go up to plus infinity. For negative n's, it will be z to the 1, z squared, z cubed, z to the 4, z to the 5, etc. So we are going to have a z polynomial in the end. And that z polynomial have nothing but coefficients related with the signal itself. What is a polynomial? Let's remember a polynomial. over, I don't know, x, for example, we know that a polynomial is something like ax cubed plus bx squared plus cx plus d. But this one goes further to the negative powers as well, plus ex to the minus 1 plus fx to the minus 2. For instance, this is a polynomial. And the above expression for the z transform will be a polynomial in z, not x. It will be a polynomial in z. But what are these a, b, c, d, etc.? What are these coefficients? Look at the formula again. The coefficients are here. They do correspond to the time signal itself. So, let's start with the first example then. It's our first signal, but this signal I didn't like much. Let's make it extending to the negative side, like this. This is 1, this is 2, this is 1, this is minus 1. At minus 1, minus 2, and minus 3. The others, if I don't indicate, they correspond to 0. So this is a discrete time signal, x of n. Now, can you write me the z transform? It's nothing but writing the same signal in the form of a polynomial, z polynomial. This representation could be imagined as a vector representation, a vector from minus 3 to 0 with 4 elements, a vector with size 4. But a polynomial is also an alternative representation to that. What is the polynomial? That polynomial will give you the z transform, as simple as that. So, what is x of z? Can somebody tell me, term by term, each of the top summations? Because it's a summation for all n. But of course, if x of n is 0 for several n, just don't indicate them. Only the non-zero coefficients will contribute to this x of z. So what is it? It is minus 1, which is this value, times z to the power 3, minus 3, plus 1 times z to the 2, or z squared, plus 2 times z, plus 1 times 1. Z to the 0 is 1. Anything to the power 0 is 1. That's automatic. So this is a polynomial. Let's write it again in a cleaner way. It is minus z cubed plus z squared plus 2z plus 1. And that is x of z. Now, as you see, or as you should see, you have to notice the signal itself in this polynomial. The polynomial coefficients indicate the signal. Minus 1, 1, 2, 1. Like that. In the same order as the polynomial itself. In a decreasing polynomial, of course. If you go further towards right, okay, let's make it a little bit more complicated and put, so this is 1 at 2, let's put a 2, an extra coefficient, another coefficient. Then we have another term, we should have another term. What is that? Plus 2 times z to the minus 2. So it will be 2z to the minus 2. An extra coefficient should be necessary over there. You have to just be careful about the gaps, of course. For example, between 1 and z to the minus 2, there is a z to the minus 1 term there should be. So you have to automatically assume that that is 0 times z to the minus 1, which means if there is nothing in between, there is a 0 value between them. So the polynomial may or may not be following the order. Okay, there may be gaps in the polynomial, but eventually it will be a polynomial. If it's a finite sequence signal like this one, then it will be a finite polynomial. If the signal is infinite extent, then the polynomial will also be an infinite extent polynomial. By the way, if we say that our x of z is like this, we will be interested in the poles and the zeros of that. The zeros will be the roots of this polynomial. Simple. Zeros, poles will be points that make the polynomial value infinity. So what is a value which makes this polynomial, what is the z value which makes this polynomial infinity? Zero, exactly. There is a pole at z is equal to 0. Why? Because when z is equal to 0, z to the minus 2, which is 1 over z squared, will be 1 over 0. So there must be a pole at 0. This one has a pole at z is equal to 0. Fortunately, z is equal to 0 point will not be considered as a finite point on the z-plane. So we will see that, or you can safely assume that, in fact, there is no pole for this one. There is no reasonable pole on the z-plane, in other words. It's only at z is equal to 0, and z is equal to 0 is a point which is excluded normally from the z-plane. Just like z is equal to infinity. There may be, you can also say that a value which makes this thing, this polynomial infinity, is z is equal to infinity. So there is another pole at z is equal to infinity, isn't there? Because when z is equal to infinity, z cubed or z squared or z itself will also be infinity. So we have another pole at z is equal to infinity. Z is equal to 0 is a point like z is equal to infinity that are excluded from the normal z plane of our interest. We'll be interested in the poles on non-zero and non-infinity values of z. So this is an example of finite signals, finite extent signals, z transform. Now, you know convolution, right? How did we perform convolution? We were flipping around one of the signals and sliding over the other one, and the overlapping things are multiplied and accumulated, and with respect to the shift, you assign the values of the convolution output, let's say y of n. Now, there is another way of understanding what a convolution means, and it comes from the convolution versus multiplication property. Do you remember that if you convolve two signals, you multiply their Fourier transforms, or you multiply their Laplace transforms in continuous time? Now, the same property holds here. If you convolve two signals, then you multiply their z transforms. That's also a property, and an easy one, an easy property. Now, at the right hand side of it, let's draw a red signal like this. One, 2, minus 1 at 0, 1, and 2. So I'm going to call this h of n, let's say, on the n-axis. What is the z transform of it? It is h of z is equal to 1 times z to the 0 plus 2 times z to the minus 1 minus z to the minus 2. Minus 1 times z to the minus 2. So this is the z transform. We have the z transform of x here. We have the z transform of h here. And I say that in the convolution, you need to multiply the two. What happens when you multiply two polynomials? You get another polynomial, probably a longer polynomial. The length will be a little bit longer. What is the highest order of the polynomial which you get when you multiply x of z and h of z? What is the highest z power? The first one has z cubed, z to the 3, which is the highest, positively highest. Over there you will have the highest to be z to the 0. So when you multiply the two terms, you will again have a term z to the 3. That will be the maximum, the highest z power in this multiplication. How do you multiply two polynomials? You have to make cross multiplications, one by one. Okay, a lot of cross multiplications. And you have to combine the common z powers. If you have something like z squared in an expression, and in another expression z squared, you just have to combine those values. So what is the negative highest power that you get? This one is up to z to the minus 2. This one is also up to z to the minus 2, and when you multiply them, z to the minus 4. So the multiplication will span from z to the 3 to z to the minus 4. It will be that long. How many items are there? How many z power items you have? 8, yeah. From 3 to minus 4, including 0, there are 8. So the multiplication output will have 8 terms. 8 terms. Just write them, multiply these two, and accurately and carefully find the multiplication of these two polynomials and write it down. When you write down those things and when you plot them like these, the corresponding plot of the multiplication, what you will plot will correspond to the convolution of this one and this one. So now we have an alternative of performing convolution, right? We just transform our discrete time signal into a polynomial. We convert the other signal, discrete time signal, to another polynomial. We multiply those polynomials. And that polynomial multiplication result will correspond to the convolution automatically. So convolution is the same as polynomial multiplication. And I was quite impressed when I noticed that actually it used to be like this. I don't know how they do it right now, but there used to be some AMP files in the mathematical package called MATLAB. Okay, we're all using MATLAB. In MATLAB, they have a container called polynomial, and they do the polynomial multiplication using convolution. Just the opposite. They don't do convolution using polynomial multiplication. They do polynomial multiplication using convolution because convolution is more systematic. The algorithm to write a convolution, if you want to write a program, a C program, for example, to perform convolution, that will not be very difficult. You flip around and you slide, you overlap. So that is the methodology to apply polynomial multiplication, as a matter of fact, not the other way around. For humans, polynomial multiplication is quite easy to understand what it means, but algorithmically in the computer it's easier to convolve. So they do polynomial multiplication using convolution. Furthermore, let's do some more signal processing. They do MATLAB convolution not with an algorithmic convolution because it's a slow operation for long sequences. If both of the sequences are quite long, then it's not worth it. There is a faster way of implementing convolution. Can you imagine what? They apply the so-called discrete Fourier transform, which we haven't seen. We have seen the discrete time Fourier transform, but we didn't see discrete Fourier transform. It's a topic of digital signal processing. We're not going to cover that. But discrete Fourier transform is a sort of Fourier transform. So they take the Fourier transform of the first signal, which is fast, because there is the fast discrete Fourier transform, and they call it FFT, fast Fourier transform. In MATLAB there is FFT. They take the FFT of the first sequence, take the FFT of the second sequence, they multiply them term by term, because in the Fourier domain you just multiply and it corresponds to convolution. They multiply them and then take the inverse FFT, which is still fast. And the result will correspond to the convolution, which corresponds to the polynomial multiplication. So can you imagine how long the sequence is? You have two very long polynomials. You extract the vectors from them. You take the Fourier transform, the fast Fourier transforms of those, and multiply them. And then take the inverse Fourier transform and assign it to become the multiplication polynomial. A very long way, a very long path, which is faster than directly trying to multiply the polynomials. In the programming years, did you have a project or a homework related to polynomial multiplication? You should have done it. I mean, it's a very nice exercise of programming to multiply two polynomials. And now that you have an easier way of doing that, it's convolution. Convolution is easier to program than polynomial multiplication. Well, anyway, so this is a finite example about Z transforms. So Z transform is nothing but another representation of the signal itself. But if it's an infinite extent sequence, this alternative representation, which is a polynomial, will correspond to a series sum. And things will become a little bit more compact. And I will continue with that example now, which is this. X of n is equal to a to the n u of n. Now this one is truly an infinite extent sequence. It starts from n is equal to 0 and goes to n is equal to infinity. And what is the Z transform of it? And the Z transform is, by definition, this infinite summation, n from minus infinity to infinity, for all n in other words, x of n, which is a to the n u of n, z to the minus n. That is the formula that we have. The same summation over n. It's not over n anymore. Because of this u of n here, it forces this n to start from 0 and go to plus infinity. It's not from minus infinity anymore. So n is from 0 to infinity. A to the n, and u of n in this range is 1, so we don't write it. Z to the minus n, or n from 0 to infinity. How can we combine these two terms in this multiplication? It is a times z inverse to the power n. Do you agree with this? And that is an infinite series summation. Just call a times z inverse is equal to, I don't know, alpha. Then it's a summation n from 0 to infinity, alpha to the power n. And we know what it is. If it converges, of course. This expression is equal to 1 over 1 minus alpha. So, this thing here is 1 over 1 minus a z inverse. And that is really the Z transform. You can box it. But are there any poles and zeros? What is a pole? Let's look at the poles first. It may be easier to find the poles, in fact. What could be a pole? Yeah, the denominator must become 0. So a z inverse, can it become 1? Yes. When z is equal to a, it will become a over a, and that is 1. And 1 minus 1 is 0. As you see, the way to understand the pole is not very complicated, but it may be easier if you just expand the whole formula into a simpler format to directly see what the pole can be. Let's multiply the numerator and the denominator by z, and then we will have z over z minus a. So it's now easier to see that z is equal to a is a pole. But nevertheless, in the previous representation, it's also possible. And this is enough. This is the correct answer. If you just indicate it this way, it's even better. But that new representation now yields us the fact that z is equal to 0 is a 0. Because the numerator is z. So when it becomes 0, then the whole system becomes 0. Previously, maybe it was a little bit more difficult to see that z is equal to 0 was a 0. But it was. Because when z is equal to 0, 1 over 0, z inverse, will become infinity. So we will have an infinity in the denominator. 1 over infinity will be 0. But it's more complicated to see it that way. Probably we see it better now, that z is equal to 0 is a 0. Is a 0. Z is equal to a is a pole. Now, what could that pole mean in terms of regions of convergence? Now, we can come up with the similar concept of so-called region of convergence, just like the Laplace transform, but it's the whole idea. If I said that the left-hand side expression, this one, converges to this as an infinite series sum, if it converges, when does it converge? When does it converge? So let me write it again here. Summation n from 0 to infinity a z inverse to the power n. When does this expression converge? It converges as long as the alpha, I said that a z inverse is alpha, as long as alpha is less than 1. The magnitude, the size of it is less than 1. Then it will be a convergent series sum. What would happen if alpha is greater than or equal to 1? Then that summation will be equal to infinity. Right? So that's a problem. We will say that it converges if a times z inverse magnitude, this alpha thing, is less than 1. Then our result will be correct. Otherwise, what I wrote as a result was incorrect. I mean, I was lying about the convergence. I was just assuming that it was converging. But it converges only under this circumstance. And that means something. It says that a z inverse in magnitude is less than 1 means a z inverse magnitude is less than 1 because they are in multiplication form. And so z inverse is less than a inverse. I'm just complicating things perhaps. It converges if the magnitude of z is greater than absolute value of a. So a z inverse magnitude is less than 1, the top one is correct, if the magnitude of z is greater than a. What is the magnitude of z? We have already given a name to that, but we didn't know it. It's somewhere here. What is the magnitude of z? Yes, exactly. It's the radius, r. So the region of convergence will be with respect to r is greater than, or r is less than, or r is in between some values. That's what we will come up with. R is greater than absolute value a is our region of convergence. Now, it's a radius. So can we really plot this region of convergence? Again, this is the real and the imaginary axis, because it's a complex plane, the z-plane. And at z is equal to a, you remember that? We had a pole. Z is equal to a is, let's say, here. That is the value of a. What does r greater than absolute value of a mean? Absolute value of a is the same as a for this case, because a is positive. I mean, I've just drawn it positive. And this is a radius. So we need to draw a circle. And I'm going to draw it with dashed and dashes and dots like this. Radius is greater than that is a region out of that circle. So out of it will be the region of convergence. It's a little bit different from the Laplace transform, because in the Laplace transform, if something is greater than something, if sigma is greater than something, we just draw it to the right of it. But now we draw to the out of a circle. And the radius of that circle is determined by the position of the pole. Notice that if a is not a positive value, but a negative value, if that is the case, then a will be where? Here? No, it will be here. But the radius or the circle will be the same, exactly the same. And it will still be out of it. That's why radius is greater than absolute value of a doesn't really care about the sign of a. The radius will still be a positive magnitude, and you will have to draw a circle. If you have this kind of a radius or this kind of a radius, which are the same. In fact, that a could even be more complex. It could be here, here, or here. Still the radius will be the same. And the circle will be drawn over there, and your region of convergence for this example will be to the outside of that circle. Now, let's remember our Fourier transform knowledges. We said that this thing converges, the Fourier transform exists if a is less than 1. Because if this a is greater than 1, then it will be like 2 to the power n. And 2 to the power n is a growing exponential. But if it is less than 1, like 1 over 2, then the summation will be 1 over 2 plus 1 over 4 plus 1 over 8, etc. So it will be a converging series, and it will have a Fourier transform. So a must be less than 1 in magnitude. What does that mean in the region of convergence? It means a is somewhere here and 1 is somewhere here. It must be. And then you draw a unit circle with a radius 1. That is the definition of a unit circle. Which is this. This is the unit circle. The necessary condition for the Fourier transform to exist, and the sufficient condition, is that this unit circle lies or stays inside the region of convergence. So if this is the situation, it is indeed in the region of convergence, which is out of a circle. And therefore the Fourier transform exists, we will say. The unit circle is inside the region of convergence. And it happens if a is less than 1 in magnitude. If a is greater than 1 in magnitude, if 1 is here and a is somewhere over there, then out of that that circle will not include the unit circle. The unit circle will be out of the region of convergence. The region of convergence everywhere there, and unit circle is inside a portion where it doesn't correspond to the region of convergence. Then the Fourier transform will not exist. That's why if a is greater than 1 in magnitude, the Fourier transform doesn't exist. The existence of Fourier transform, or if you say Fourier transform exists, means that if it's a system impulse response, if it's not a signal, if it's not x of n but h of n, for example, then it corresponds to a system. Then we say that the system is stable. Because a system or a signal are the same things. A signal is notated by x of n, a system is notated by an impulse response, which is h of n. And the z transform of x of n is x of z, the z transform of h of n is h of z. You just need to say that for h of z, if the region of convergence includes the unit circle, then that h of n, that system, linear and time invariant system, is a stable system because its Fourier transform exists. So that's a very nice way of checking. The same check also exists in continuous time as well. Then, from h of t, you look at h of s, its Laplace transform. And if the region of convergence includes the j omega axis, sigma is equal to 0 axis, j omega axis, then you say that the system is stable because the Fourier transform exists. J omega axis is included. Therefore, the system is stable. Okay. So this implies two things. In continuous time, j omega axis is inside region of convergence. In discrete time, unit circle is inside region of convergence. In fact, unit circle and the j omega axis are the same things, aren't they? Remember that z is e to the s, e to the sigma plus j omega, in other words. If sigma is 0, then it is the j omega axis. Then z will become e to the j omega, and e to the j omega is equal to circle. So in continuous time, we have sigma plus j omega converted to discrete time. Z is equal to e to the sigma plus j omega. Therefore, the j omega axis, which means sigma is equal to 0, will be translated as e to the j omega unit circle, because that would be e to the 0 plus j omega. When sigma is equal to 0, e to the sigma plus j omega will be e to the 0 plus j omega, and that is the unit circle. So there is a mapping in the shapes from the Laplace to z plane, and that is a warping. You have stripes on the Laplace plane, remember that? And those lines or stripes, vertical things, are rotated into the z plane. This is the j omega axis rotated and bent to form a unit circle, for example. It's a mapping like that from s to z. Everything that is straight becomes rotated in the z plane. And everything to the right of a line will become to the out of a circle. Everything to the left of a line will become inside the circle, an area inside a circle, and things like that. We will see, of course, more examples with respect to that. It may be a good idea to increase the number of examples. And now I'm gonna show you, for this hour's last example, an awkward example and a surprising one, and then you will see why we need the region of convergence, just like why we need the region of convergence in the Laplace case. Now this minus a to the power nu of minus n minus 1 That minus 1 is a shift, but u of minus n is a negatively expanding sequence. Okay? So, first let's think of this. When does it converge? For which values of a do we have a convergent sequence? Less than 1. If a is less than 1, think of it like this. Then it will be a decaying exponential. Okay? And this thing, u of n, is expanding to the left-hand side. So if a is less than 1 in magnitude, then it will be increasing in that direction, towards left. That's a very bad idea. Just the opposite. A must be greater than 1 this time. If a is greater than 1, then it will be an increasing exponential, but we are taking the left-hand side portions, the small ones, the small values. The larger values appear at positive indices, and u of minus n will not have them. U of n will have them. So a must be greater than 1. Now, is that really the case for this? First of all, what is x of z? Let's first calculate what we have. This, I will skip some details, will be n from minus infinity to 1 because of this u of minus n minus 1, because its span is from minus infinity to 1 to minus 1, excuse me. Minus infinity to minus 1, a to the n, z to the minus n is what we have. And we can also write it as n from 1 to infinity by making a change of variables. N is equal to minus n. A to the minus n, z to the n. Or if you're uncomfortable with using the same name as the changed variable, then you can say m is equal to minus n. It will be m from 1 to infinity, a to the minus m, z to the m. Okay? That is the same thing. And since it starts from 1, it misses one term, and that one term is equal to 1, because when n is equal to 0, z to the 0 will be 1, and a to the 0 will also be 1. So we can write it like this: n from 0 to infinity, a inverse z to the power n. This new extra term of 1 comes from the fact that I have to eliminate the one which starts from 0, and I have to put it back. So what is this summation equal to? That summation is 1 minus 1 over 1 minus a inverse z. And I'm again assuming that this thing is alpha, and that alpha is, let's assume, smaller than 1. So 1 minus 1 over a inverse z is what we get. And if you just combine the results, you will get 1 over 1 minus a z inverse. Quite interesting, isn't it? I mean, if you just carry out the calculations, this is what you will get, which is the same, z over z minus a. This is a deliberate example which gives you exactly the same result as the previous example. Didn't we have a similar situation in the Laplace transform? We had a right-hand sided solution and a left-hand sided solution, and they both have the same Laplace transform. It's the same case here. We have a right-hand sided solution signal or a left-hand sided signal which have the same z transform, which is z over z minus a, as we see here. But for our case, alpha is different, and its convergence will require some different region of convergence. Alpha is equal to a inverse z, so magnitude of a inverse z must be less than 1. This thing must converge, which says that z is less than a in magnitude, or r is less than a. So it's just the opposite. The other one was R is greater than magnitude of A. This one is R is less than magnitude of A. And the way to plot it will be quite easy. We'll just indicate the point of A. We will draw a circle with that radius. I'm drawing it with dots because that boundary is not included. It is strictly less than A. It's not less than or equal to. And then we draw the region of convergence, which is R less than that, inside the circle. This is the region of convergence. When you compare it, when you compare it with the previous one, it was out of the circle. Now it's into the circle. And for this one to exist, for this one to be stable, or the Fourier transform to exist, the conditions are just the opposite. This A must be greater than 1. Because if A is greater than 1, then 1 is somewhere here. And when you draw a circle, that will be your unit circle. It will be inside the region of convergence. If A is less than 1, then 1 will be somewhere there. And when you draw a unit circle with a radius 1, it will be out of the region of convergence. And the Fourier transform will not exist, or the system will be unstable. So the answer to my previous question is A must be greater than 1 this time for the convergence of this awkward signal. So the trick is the same. We will have some Z transforms. For example, I will give you a Z transform and say that it is this. And ask you, what is the time domain signal? What is the inverse Z transform? You have to then decide, is it this signal or this signal, which is the answer. You have two choices, and you will have to choose according to the region of convergence. If the region of convergence is R greater than the pole, out of the pole, then you have to choose the right-hand sided solution, which is this one with the box, the right-hand sided solution. If it's out of a circle, if it is inside a circle, like this, then you have to choose the left-hand sided solution, which is given with the box over there. So it's the same trick. To the right or to the left is reflected to out of a circle or inside a circle. You have to choose the right-hand side and left-hand sided solutions like this. Okay? Now let's give a 15 minutes break. After the break, we will continue with some examples.